we have an array A. We already sorted 2, 4, 5, and 1, 7, 3 to be sorted, and currently we are sorting 6. So the index I indicates that the current count being inserted into the hand. So at the beginning of each iteration of the for loop, which is indexed by I. So we have the subarray, which is a contiguous portion of the array, which consisting of elements A of 1 through A of I minus 1 constitutes the current sorted hand, and the remaining subarray elements A of I plus 1 through A of n, which corresponds to the pile of hand still on table. So in fact, the elements A of 1 through A of I minus 1 are the elements that originally in the positions from 1 to I minus 1, but now they are in sorted order. So we state these properties of A of 1 through A of A minus 1 formally as a loop invariant. So here is the operation of the insertion sort A and n. So in this insertion sort algorithm, we have two input parameters. Well, A represents the array that needs to be sorted. Initially contains the sequence 5, 2, 4, 6, 1, 3, and n is 6 in this case, which is the size or length of this array. It tells the algorithm how many elements are in the array A. The array indices appear above the rectangles, and the values stored in the array positions appear within the rectangles, and the step A to E is the iterations of the for loop, and in each iteration, the orange rectangles holds the key which taken from A of I, and compare it with the value in the blue rectangles to its left just by the code, well, j is greater than 0 and A of j's value is greater than key's value. And then we use blue arrows shows the array's values moved one position to the right just by the code we assign A of j's value into A of j plus 1. And we also use orange arrows indicates where the key should move to, which by the code we assign the key's value at A of I plus 1 position, and F step is our finally sorted array. At the start of each iteration of the for loop, the subarray A of 1 to I minus 1 consists of the elements originally in A of 1 to I minus 1, but in sorted order, right? So the loop invariant helps us to understand why an algorithm is correct. So first is initialization. Something is true prior to the first iteration of the loop. And the second is maintenance, which if it is true before an iteration of the loop, it remains true before our next iteration. And the third is termination. The loop terminates, and when it terminates, the invariant, usually along with the reason that is the loop terminated, which gives us a useful property that helps us show the algorithm that is correct. And when the first two properties hold, the loop invariant is true prior to every iteration of the loop. Let's see how this property holds for insertion sort. So first is initialization. We start by showing that the loop invariant holds before the first iteration. When I is 2, the subarray A from 1 to I minus 1 consists of just a single element A of 1, which is the fact that the original element in A of 1, and moreover, the subarray is sorted. After all, how could a subarray with just one value not be sorted, right? Which shows that the loop invariant holds prior to the first iteration of the loop. And next, we tackle the second property, which is maintenance, which showing each iteration maintains the loop invariant. Informally, the body of the for loop works by moving the values in A of I minus 1, and then A of I minus 2, and then A of I minus 3, and so on. So just by one position to the right until we find the proper position for A of I, at which point we can insert the value of A of I, which is assign the key's value into A of j plus 1, and then the subarray A of 1 to I consists of the elements originally in A of 1 to I, but in sorted order at this time. And then we incrementing I, which is increasing its value by 1 for the next iteration of the for loop, which can preserve the loop invariant. And a more formal treatment of the second property, would require us to say and show a loop invariant for the while loop, while j is greater than 0 and a of j is greater than key. And then we assign a of j's value into a of j plus 1, and then we decrement j's value by 1. And finally is our termination. We examine the loop termination. The loop variable I starts at 2 and increases by 1 in each iteration. So in the for loop for I is 2 to n, once the i's value exceeds n, the loop terminates. That is, the loop terminates once I is equal to n plus 1. We substituting n plus 1 for I in the wording of loop invariant yields that the subarray a of 1 to n, which consists of the elements originally in a of 1 to n but in sorted order. Hence the algorithm is correct.